1.
Hi, I'm John from Divers Den, Georgia. Compiled a video today about Boyle's Law, mainly because I would like to explain Boyle's Law for those who really don't understand it, and provide different, teaching methods for instructors or dive masters. For if you're looking for different ways to teach, I like to go around and look at the way other people teach because, like to see the way people teach and see the tools from them. So if you came across this video on YouTube, hopefully you can learn something from me. So I'm going to get right into it. So Boyle's Law describes a relationship between pressure, volume, and density of something in a flexible container. Sometimes they describe it with an upside down bucket with the air getting compressed by the water entering the bucket, but I'm going to strictly stick to a flexible container like a balloon. It could also be something like your BCD or your dry suit, or more importantly, your lungs. It could be a lift bag too. All right, but I'm going to try to do it in 3 phases. The first phase, I'm going to try to talk about it qualitatively, right, just with some aero analysis and things like that, so you can, fundamentally grasp the relationships between all of them. Then I'm going to talk about it quantitatively, so you can kind of see how it relates with diving and how much a change in one will change it in other with by a factor of how many. And then we'll show you, we'll demonstrate visually with an experiment that we have. All right, so say for instance I have a volume of something, right? Say that's my flexible container, and it has so many molecules of a gas inside of that, right? And if I have this many pressures of force pushing down again, we're going to call that pressures of force. We're going to call it atmospheres. Right now, atmospheres is just one unit of measuring pressure. It can be in pounds per square inch, it can be in bar, it can be in feet of water. If you want to talk about in feet of water, it can be in anything you really want to measure it in. But when we're talking about diving, we normally talk about it in atmospheres if you're over in the United States, or bars if you're over in Europe. 1 atmosphere is equal to 1 bar, and 1 atmosphere is approximately 15 pounds per square inch, right? So if I have like 1 atmosphere, on the surface, and we'll say that that's exerting that much pressure on the outside of this container, right? So if I increase the pressure of the exerting on the outside of this container, right? So let's add some arrows showing that the pressure is going up, right? Then, because it's a flexible container, then my container is going to shrink, right? Because it's flexible, but I still have the same number of molecules inside that volume. I didn't have a way for it to escape or to add a number of molecules. So what happened to the characteristics of this, this balloon, right? So the volume went down, right? And the density went up, right? So this means that, density and pressure are directly proportional. So pressure goes up, density goes up, and that pressure and volume are inversely proportional. Right, so as pressure goes up, volume goes down. Right, so it's kind of like that. Right, and that's air analysis. It's pretty easy to understand, and of course the contrary is true. So if I had all this pressure exerted on the outside of this flexible container, and I removed some pressure, I have this eraser and I'll use it, right? Remove some of that pressure, right? All my pressures would go down, and then therefore all my density arrows and volume arrows would flop direction. So my volume would go up, my volume would go up, and all those molecules of the gas would have more room to spread out, and therefore density would go down, right, and volume would go up. Okay, so that is how Boyle's law works qualitatively. It's pretty straightforward there. So quantitatively, it's a little bit harder to grasp because it has numbers and things, but it's not too hard to understand once you understand, you know, pressures, atmospheres, and you know how much water weighs is in relationship to the 1 atmosphere of air. All right, so at the surface of the ocean, there's 1 atmosphere, and that's pretty intuitive, right? Because that's where the baseline is 1 atmosphere, because there's 1 atmosphere of air that weighs on top of us, right, on the top of the ocean. And it just so happens to be 14.7 psi per square inch, right? But you know, that's not that important, right? But we'll remember that for our experiment a little later, but we're gonna round that up to 15 pounds per square inch, right? Just because it's easy math, okay? And then every 33 feet of seawater, just so happens to be so dense that it's equivalent, the weight of it is equivalent to another atmosphere. So it's 2 atmospheres total. Right? 1 atmosphere plus 1 atmosphere is 2 atmospheres. Right? And then if I went an additional 33 feet of salt water for a total of 66 feet of salt water, right, I'd be at 3 atmospheres. And it's pretty straightforward here. And we'll go down all the way down to 4 atmospheres for fun. Right, 1 atmosphere, additional 33 feet for a total of 99 feet of fresh water. Salt water, sorry about that. Right, so it's pretty intuitive here to see how that whole thing works, okay? So if I'm at 1 atmosphere here and I go down to 2 atmospheres, right, the atmospheres doubled. So if I had a volume of, we'll say 1, you know, we'll say 1 cubic foot, right? It's pretty easy to make, that's a pretty easy unit. 1 cubic foot, 1 cubic foot, right? And I took it down to 2 atmospheres, right? It'd be 1/2 cubic foot, right? And then the density would have gone up by 2, right? Whatever the density is, will, you know, if I took that down an additional 33 atmospheres, you compare it to what it was on the surface, right? So it'd be 1/3 a cubic foot as compared to what was on the surface. And then down here it'd be 1/4 a cubic foot as it was compared to the surface. And the density would be 4 times as dense, 3 times as dense, and then 2 times as dense as it was on the surface, right? So this is important when it comes to air consumption rates, because as you descend, you can see that because it's 4 times as dense and 3 times as dense, each breath that you take, I mean, your lungs don't change size, right? I'm on the surface right now and I take 1 breath out, you know, that's the size of my lungs. If I go down to 100 feet, you know, it still takes me that much air of my lungs to fill, right? But it's 4 times as thick. So it's gonna exhaust my air supply 4 times faster. So new divers are often surprised by the rate at which you consume your gas. that's one of the reasons why it requires advanced training to go beyond 66 feet because the accelerated gas consumption rates, coupled with some other things, but that's beyond the scope of this lecture. Right, so that's quantitatively how this whole Boyle's law thing works. And then conversely, here, if I were to just go ahead and do this in reverse real quick, say I had a balloon and I filled it up at 1 cubic foot right here, and I took it all the way to the surface, it would be 4 cubic feet all the way to the surface. All right, so that's pretty important there, because if that was a balloon or a lift bag that was only rated, it was a 10 cubic feet, it was only rated 10 cubic feet, and I took it all the way to the surface, and then it was 40 cubic feet on the surface, I'd be spilling air out the bottom of that lift bag, and it would start shooting up really quickly if I didn't vent it off. And then more drastic things can happen, and I'm going to show you that here in a minute. So that's pretty important to understand. You have to vent off things, and if I have a BCD that's full and I start ascending, right, here is the biggest change between 1 atmosphere and 2 atmospheres. It doubles, or it takes 1/2 in size. And then from here to here, this change is not nearly as big from here to here. So people, hang out right here at their safety stop, right, and they do an awesome 3-minute safety stop, and then they ruin it by, going from 15 feet to, 1 app to the top. But this is a huge change in pressure, but they don't really realize it. This is the biggest change in pressure of your entire dive. But I digress. Okay. So that's that. So we're gonna go ahead and move over to the experiment here. Inside here I have a jar. There's a computer that'll turn on as soon as I pressurize the jar, and that'll show you the feet that is simulated inside the jar, the depth that is simulated inside the jar. Up here is the pressure in pounds per square inch. Remember, every 15 feet or so is 1 atmosphere. It shows it at 0 atmospheres or pounds. Just keep in mind that right now it's at 1 atmosphere because this is gauge pressure, not absolute pressure. So gauge pressure is 1 atmosphere. So it's actually 1 atmosphere now, and every 15 pounds is going to be actually the 2 atmospheres. But you'll see the depth here, and then I have a balloon in there that's going to represent my closed volume, and we're going to say our lungs here, and then we're going to go ahead and show you what it's like. First, I'm going to go ahead and inflate, take a normal breath at the surface, and then we're going to take it down to 33 feet, and we're going to show you that it's half the size as it was at 33 feet, and then we're going to take it down to 66 feet, and you'll see that it was about 1/3 the size as it was on the surface. So let's go ahead and do that real quick. Okay, so I'm going to go ahead and turn my air on. All right, so my air to the unit is on, and I'm going to go, you'll see the computer turn on when I blow up. I'm going to take a normal breath on the surface, and normal breath is going to be, we'll do that. That's a normal breath. You think that's good, Justin? Pretty good? Okay. So that's my normal breath on the surface, and it shows I'm at 5 feet on the surface, and I'm still, almost 0. So yeah, I'm just not going to go into the details there. All right, so if you watch the pressure gauge and the depth gauge, I'm going to go for 15 pounds, and you'll see the depth gauge go to about 33 feet. I'm going to slowly do that. And I'm at 16 feet, 4 feet. And it's going to bounce a little bit as pressure stabilizes. And I'll bring it back up. And you'll note that the balloon is about half the size as it was on the surface. So now I'm at 33 feet exactly. Can you see that pretty good? All right. So next I'm going to go ahead and I'm going to increase the pressure to 66 feet. Oh, that's the wrong valve. Go ahead and go to 66 feet. And you can see the balloon shrinking. And it is about a third the size as it was at the surface. Okay, and then if I were to depressurize the whole system, I would return. The computer's going to freak out right now because it's going to exceed my ascent rates, but it's going to return to the normal size. Slowly ascend once I start venting it. Okay, and here we go. I'm not putting any air in the balloon. It's just venting pressure from the pressure vessel, and the balloon is expanding because the air inside the balloon is expanding. The density is going down, and it's going to return to the normal size that it was when we started. Okay, now we're going to show you how this principle can be dangerous. All right, so say this is again my breath on the surface, and I descend. I'm breathing normally, but I descend to 33 feet. Turn the air back on. I descend to 33 feet. I get to 33 feet, and I take a normal breath, and I fill my lungs back up to the normal size. Okay, and then I descend back down to my normal, limit of my open water recreational diving at about 60 feet. Okay, and then something happens. I run out of air or I panic, and I hold my breath while I ascend to the surface. Right, the air doesn't have anywhere to expand to, and I just ascend to the surface at a quick rate, and so I'm already going to be bent. My dive computer is going to be freaking out on me, but what's more important, what's more dangerous, is I don't exhale while I'm ascending. Maybe I'm doing a controlled emergency swimming ascent. You can see that the balloon is expanding. My dive computer is telling me to slow down, and as I ascend, the air is getting, my lungs getting beyond the normal capacity of it, and it gets to the point where it's way beyond the normal capacity. Okay, it looks like I didn't blow it up enough, so let's redo that again. Didn't get the full effect that I wanted. All right, so let's take that down to 100 feet. This will be a better demonstration too. Oops, that's the wrong button. So we'll take that down to there, and let's go ahead and blow it up to the normal size that was. This diver had bigger lungs than I thought he did. All right, so that's a normal breath, and we'll turn that off. And he's at 105 feet right now. We'll make sure I show what happens here. So now we're descending. Same scenario. There it is. That was at 71 feet. So as he's ascending, the lungs, filled up and continued to expand, and the alveola ruptured, and that's called an arterial gas embolism, and that's one of the most fatal things that can happen to a diver. So hopefully you learned a thing or two in this, and if you have any questions and you liked it, go ahead and comment in the section and click the like button. Thanks a lot.